I haven't bought my ticket, but Patricia Oliveira says that I don't have to. So we'll see. I'll show up, and then if they make me pay, I've got money. So anyway, yeah. So what we're going to be doing is we're going to be taking Taylor polynomials. I know, joy, right? We're going to go back to Taylor, but don't worry. It's not going to be that hard. And we're going to use those Taylor polynomials to generate these methods, the methods for solving these differential equations. So just to remind you, what we're looking at here is you have, let's see, can I find a blank slide? I can. Okay, so here's what we're looking at is you have some sort of a differential equation. We can take something simple for now if you'd like t plus y. So now you're sort of familiar with this. If you're still not exactly sure what this means, maybe we can explain as we go forward. And you'll have something like this: y of 0 is equal to 2. So this is the differential equation. So differential equation. Oh, I just realized I assigned you homework as well. Sorry, I'm out of sorts today. And this is the initial condition. Condition. Okay, so now that I've reminded myself, if there are any issues with the homework, we could talk about those. This is next time's homework. Let me find today's homework. It was just a few pages before this. There we go. Okay, so on today's homework, you were to practice this idea of like, do you know the degree of a differential equation? And then can you verify that a function is a solution to a differential equation? So if you did those things, I feel like those two, and then this was basically the same thing, verifying that a function is a solution to an initial value problem, really the same thing. Was there anything about any of this that it was confusing? Because if you understand that, then I think you can understand what we're going for here. The goal is to somehow come up with the solution without going through the trouble of taking a class in differential equations, which some of you haven't done. Wow, no one's got any issues. Okay, that's fine. So anyway, so this is sort of the basis for the thing. And so what it means to be a numerical solution is that we've got our differential equation, we have our initial condition, and we want to know what's going to happen in the future. So what does the future look like? Of course, that is the question, is it not? Especially if you're a senior or if you don't know what's going to happen in the fall. It would be nice to know. So let's make a prediction. So we want to know, so here's what we want. We want to know what is y of 2, let's just say. So y of 2, we can pick this is just arbitrary, but what's y of 2? And so the idea here is we're starting at 0. Here's 2 over here, and we're going to pick some sort of a step size. Maybe our step size will be 1/2, but we'll get to this. Don't worry, we'll go through the details. But the general idea is that you're going to take this and you're going to take little steps, and each of those steps are 1/2. And then you'll do another step, and each of these steps will be educated guesses about the future based upon what we know. Of course, it's not going to be a perfect prediction. And then maybe this will be the next step, and then the final step. And so what's going to happen at y of 2? Well, there's my prediction right there. There's the prediction. And of course, if we have analytic methods, which some of us do because some of us have taken differential equations, you could actually compare your prediction with the actual truth about what that future would look like. But of course, in general, when you're dealing with differential equations, oftentimes the differential equation is too complicated to solve analytically, and so we're stuck with trying to make predictions and hoping that they're close. So we're going to be talking about the prediction methods, and then we're going to deal with the how close are we. So we'll deal with the prediction methods first. So the prediction methods are all going to rely, at least today, on Taylor polynomials. So I need to remind you of this. So let's do a quick reminder of how to make a Taylor polynomial. So let's do a Taylor polynomial for the function f of x is equal to, we don't want to make it too hard, do we? How about e to the x squared? And we want to have around x0 is equal to 1. So let's do that. And let's just do the t sub 2. We don't want to make it crazy. So t sub 2 just means it's going to be a second degree polynomial, Taylor polynomial. So in other words, I'm just going to have the 0, the 1, and the 2. I'll do the 0 for you, the 0, 1. What that is that will be the function. Let me remind you kind of, this is what we did. This is way back, like the very first week. A lot of you didn't like this. Sorry, we got to do it again. So anyway, so this is the function. You did something like this. So e to the x squared. I'll make this little line here. And then, so this is the function, and then this is the function evaluated at the point. And this is x0 is 1. So this will just be e. So what we're going to need to do is we need the derivative and the second derivative, because in here is 2. So I need 2 derivatives. This will give me a chance to at least say that I'm going to do attendance. There we are. I have to log in again. They keep making me do this. Uh-oh. Sorry. That was weird. I've never seen, there's a screen that popped up that I've never seen before. But now I'm back to attendance. Sorry about that. Let me pull up attendance. You go get your derivatives. I know. You're going to have to use the product rule. You just do it. It's going to be fine. Numerical methods, do my attendance, and then I'll pick someone at random. Let's see, you're not here and you're not here. Okay. Done. Okay. Random. All right. All right, Eli. Eli, do you know the derivative of e to the x squared? Very good. You said 2x e to the x squared. Is that what you said? That's what I thought. Okay, yeah, so Eli correctly said, well, the derivative of e to the x squared is just e to the x squared. But the chain rule says take that function and do the derivative of that. And so the derivative of x squared is 2x. Very nice. So 2x e to the x squared. Now I'm going to get f of x0, and my x0 happens to be 1. So this will be 2 times e. So 2e. That's my f of x0. Now let's just do one more. And then don't worry, we're only going to do one of these, and then you'll hopefully see how this relates to the differential equations. Okay, the final one, we need a derivative. Let's see who gets to do this derivative. Sam, do you know the second derivative? Can you do the derivative of that derivative? You said 4x squared e to the x squared. Very good. It's the product rule. So what Sam just did was he did 2x times the derivative of e to the x squared. Now he's going to do the derivative of 2x. What's the derivative of 2x? Okay, yeah, she said 2, so I'll go with her answer. So yeah, it's 2. And then don't mess with the e to the x squared. So yeah, it's the product rule. I know it's been a few years for some of you since you had calculus, but that's the product rule there. Not a big deal because we're just going to, yeah, we're not going to be, this is probably why that first couple of weeks was rough. Okay, now I'll plug in x equals 1. When I plug x equals 1 into here, what do I get? I get 4 times e plus 2 times e. That's 6 times e. Sorry, where is it? Where's my work here? Whoops, there it is. So 6 times e. 6 times e. Okay, good. So here's the deal. The second Taylor polynomial, I'm using this formula, but it's really pretty straightforward. You take these as your coefficients, so e, 2e, 6e. Those are going to constitute the coefficients. I'll even write them down like this, e, 2e, and 6e. But then don't forget that you have to multiply by this. Now that first one, that e, I'm not going to multiply it by anything because the j is 0 for that. But then I do times x minus 1 to the first, and then x minus 1 to the second. So technically, I could multiply e, the first e, by x minus 1 to the 0, but whatever. And then notice I have to divide by j factorial. So I guess I divide by 1. here I divide by 2. So that's the only one that I could put a 1 here. And I could even put a 1 there. 0 factorial is 1. If you don't believe me, use your calculator. And if your calculator says it's not 1, then it's wrong. So anyway, so there it is. There's the second Taylor polynomial. The reason I bring this up is because, or remind you of this, oh, they all appear at once. Let me make it not appear at once. Is that the Taylor methods for the for differential equations, solving differential equations, they are just the Taylor polynomials. We're basically going to use those Taylor polynomials. And here, I'm just going to make sure that we don't have to look at the whole thing. There, that's better. Save. And then it should update. It hasn't updated yet. Update. Come on, buddy. Update. I'm online. Oh, good. It updated. See, I knew it would update eventually. Okay, so there, let's see. Can I get rid of this? I just made it worse. Ooh. Okay, whatever. I guess the little blue square is there. I'm sorry. Wait, I think I can get rid of. Hold on. If I were there, it may magically disappear in a minute. Okay, so the Taylor, yeah, there it goes. The Taylor methods. So what they are is they take the Taylor polynomial of degree 1, 2, or 3. So here's the order 1 is the Taylor polynomial of degree 1. And I know it looks a little different than what I had on the previous slide, but here's the deal, is that you have the function value, and I'll go back to the other slide so you can see this. The function value, that's this right here, function value. And then the second thing is the derivative, basically the value of the derivative, and the value of the derivative, where is that? Where am I? Taylor polynomial is back here. Value of the derivative. Notice that this is f prime over here. That's f prime, and I put that right here, times x minus 1. Now, x minus 1, in our case, when we're thinking of the Taylor methods, that is going to become h. So that is h. You think of that as the step. You're going to take a step. So I'm standing here, and I want to know what's going to happen in the future. Well, what I'll do is I'll make a prediction about what happens about that far. I'll make a step, and then I'll make another step. And eventually, I'll get to where I want to go, but I take these little steps to get there. And so that h there, this x minus 1, that's just how far am I willing to step. There it is. So, so that is h. So that is basically the same as a degree 1 Taylor polynomial. This is also called Euler's method. This we've already done. So we've done this a couple of times. We're going to do it again in just a minute. But just to remind you, here it is back here. So we did this. I don't want to belabor it. We'll practice it as well in just a sec. So that one's Euler's method. Let's practice this with an actual differential equation. So here's what I want to do is this. Oh, actual solution. I didn't write down the actual solution. Well, if we have time, we'll get the actual solution. The differential equations people here could do the actual solution. This is a simple it's a linear differential equation, very easy to solve. But let's actually just let's do this numerically. Sorry, I don't know why I'm over here now. Copy, paste, paste, paste. Okay, just wanted to make sure I had enough space to do this. Okay, so here's how we're going to do this. Is I'm going to use Euler's. So I guess I can cross that out for now. Well, if we have time, we'll do the actual solution to compare. So we'll use Euler's method, which is Taylor method order 1. By the way, this is all we're doing today, is 3 Taylor methods. That's it. So pretty simple. So here's the way that we're going to do this. And I know we did it before. So what I have is I make a little table. I start off with, I guess we'll use, x. I have x, not t this time. Get rid of that. So we start off with x and y. And then we're going to do f of xy. And f of xy is this. Okay, so that equals y prime. And then we're just going to repeat. And because I'm using h is equal to 0.5, I only have to make 2 steps. So I tried to keep it light. So let me do the first step, and then you'll do the second step, and then we'll repeat when we do the other Taylor methods. So the first step is x equals 1, y equals 2. That came from the initial condition there. And then I've got the slope. So think of this f of xy, that's the slope, is going to be 0. Oh, okay. So I have it lucky. I've got it easy in this case. This one is an easy step to make because the formula back here says that I take, to get the next number, I take the old number plus whatever our step size is times the slope. So let's go back here and do that. So my next number is going to be the old number plus the step size times the slope. Well, that was easy. So when x is 1.5, y is equal to 2. So now your job is to take these two numbers, plug them in up here, get a new slope, and then see what the next predicted value is. So I'll give you a minute and see how you do that. So there's a couple of things you need to do. So take your time. All right, let's see how we're doing. It's not all that complicated. Sam's gone, but Zane is here. Zane, what do you get when you plug x equals 1.5 and y equals 2 into that thing up there at the top? 2.5. All right. So it's just 2 times 2.25 minus 2. Very nice. So that's the new slope. Now we're going to do the same thing we just did, 2 plus the steps. Oh, yeah, the old value is 2 plus the step size times now 2.5. Okay, let's see who gets to do this. I know it's not very hard now that I got it written down, but Briar, what did you get for your new y value? Oh, okay. Yeah, very nice, 3.25. So this is probably not the greatest prediction. In reality, you would want to use a step size much smaller than this because we have these modern computers. If you can program this into some Python, it would be easy to do 10 steps or even 100 steps. But for now, I'm going to take this big step, and then I'm at 2 again, and then I take another big step, same size, and I'm like, oh, I'm way up here at 3.25. That is my prediction for y of 2 is 3.25. Like I said, I should have computed. I guess I got distracted. I think my wife showed up and wanted to go to lunch, and I didn't actually compute the actual value. But anyway, you get the picture of how that works. Now let's just back up and see. So this is Euler's method. Taylor method of order 1 is Euler's method. So this is easy stuff. It gets a little more complicated when we go to Taylor method of order 2. This one doesn't have a special name, but I want to point out that this is exactly the same as the Taylor polynomial. Notice that you have the initial, so this is the function value plus h times the slope, and h is the difference between where you are and where you're going to be. And then this is h squared over 2, so like the 2 factorial in the denominator. So this is exactly the same as a Taylor polynomial, is where this is coming from. And this is the second derivative. Okay, so let's go and use the second order Taylor method with this. Let me rewrite that so that you can remember where it is. Whoops, got big all of a sudden. So y of x1, so the next value is the old value plus h times f. Well, here, I'll just do it this way. I'll do it the way it's written there. Let me do it. Give me a sec. Y prime, x0, y0. So that y prime, what that's referring to is that's just the slope. So what we did with Euler's method is we said, oh, y prime, there's y prime. I'm just going to put x and y into that, and I get my slope. So that's all that is. The tricky part with this second order method is, where in the world are we supposed to get this thing? Y double prime. Ooh, you got it. You know it. So we're going to take the derivative. Oh, what fun. We can do the derivative of this, can't we? Y double prime. Whoops. Sorry, it changed. There it is. Second derivative. So yeah, we need a second derivative to do this. So in other words, what's going to happen is to do, get rid of this again. To do this, I'm going to make another table. My table's going to be a little bigger. I've got x and y. I'm going to have the slope, I'll call that y prime, and then I'm also going to have the second derivative. So I'm going to have more stuff. And then, of course, I think you can see where this is going. If we want to do a Taylor method of order 3, you just tack on another term. And if we have time, we're going to do it. If not, you'll be doing it for your homework anyway. So anyway, yeah, let's see if we can get this second derivative. Go ahead and see if you can get your second derivative. Sam, you know it, but you're not here. Rachel can do it, though. Rachel, what's the derivative of the first derivative? In other words, what I've got at the top is the first derivative, so I want the second derivative. What's the derivative of that? Minus 1. But anytime you have y, because y, you remember from your days in calculus, you had something that you dreaded, which was this implicit differentiation. I know. So the main thing to remember is that the derivative of y is not 1. The derivative of y is y prime. That'll do it. I mean, technically what you would do, the way that implicit differentiation worked was if you had something like this, y squared, you would do the derivative the way you used to, what you're used to 2y, but then tack on a y prime. So that's another way of thinking of it, is that anytime you do a derivative with a y, just tack on a y prime. I kind of prefer just to think of it as, well, the derivative of y is y prime, which is true. So there, that feels better to me. Well, you know what? What is y prime? Y prime is what's up there in yellow. So I'm just going to rewrite this like this. 4x minus the quantity of 2x squared minus y. I guess that's actually overkill, I just realized, because I'm going to be filling in this table. I don't need that. I got excited about it, but I don't need it. Okay, yeah, let's go ahead and fill in the table now. So we're starting with y of 1 equals 2. When x equals 1, y equals 2. We've already done the slope. We did that on the previous slide. Okay, let's see if we can do this. The second derivative, notice the second derivative is 4 times x, 4 times 1, minus the first derivative. So that's 4. Now this is gonna, I am running out of room, so I need to get this to actually obey me. Okay, I got it. Let me just switch over to Notability where I have infinite room. I don't have infinite time though. Copy and delete. Okay, give me a sec. That's differential equations, ignore that. Oh, no, that's calculus 2, never mind. Still ignore it. Here we are. Okay, this is much better. See, I can zoom in, I can zoom out, I can move around. I got plenty of room. Okay, so now that I've got those pieces, my goal is to move myself down to 1.5 because the step size is 1.5. So I'll do this one for you, and then hopefully the next one, when we go to 2, you'll be able to do it. So with 1.5, what I'm going to do is I'm going to plug all of these things into this expression up here. So let's see, can I make it all visible? Just a sec. Here we go. I'm going to do my best. And I may have to zoom in and out as we go along, but here's how this works. Is this thing, I've got y, so that's 2, plus the step size times the slope, which was 0, so that's not very exciting, plus the step size squared over 2 times the second derivative. Now that's more exciting because what I end up with is 2.5. So that's the sort of thing that you're going to be doing multiple times. And you can see that once we have our hands on this, it's going to be easy to automate this. Really, like to do it by hand is painful. And the homework is for Monday is do it by hand, but that should prime you for wanting to do this using Python. But go ahead and do the next level. So in other words, you're going to compute y prime using these two. Where's y prime? Y prime is yellow. And then you're going to compute y double prime using this function here, kind of like what I did in purple. So take a minute, see if you can crank through all of that. Oh, wait a minute. Did I do this right? Yes, I did. Sorry, y double prime is right there. I should highlight that a different color. And then you compute the next y. Here, this is y double prime is green. Double prime, single prime. There. All right, where's my volunteers? Uh, all right, let's see where we are. Some of you are like, this is boring. You've done it all. Okay, well, let's go ahead. Grayson, what did you get for y prime with these first? So you're just using that yellow function up there. That's what I got as well. Very nice. And then once you've got that, the next one is actually quite pretty straightforward. So let's see who gets to do that. Eli, do you have that next one, the y double prime? Got 4, okay. Sounds reasonable to me as well. Interesting. Is this going to have a constant second derivative? Well, doesn't matter. We're moving on. So let's put it all together and see if you can put all of this, and I know it's kind of hard to read, but you're going to put it all into this formula right here. It's just the Taylor polynomial for this function. So see if you can you're going to stick all of these things into that. And I'll do the same thing over here, but you go ahead and do that, and then I'll see if someone has the calculation. But I'm going to write it down over here to the right, just so that you can compare. Well, as you're doing your calculation, you should have something that looks sort of like this. So, did I get everything? Yeah. Yeah, this looks good. Well, Alyssa, did you get something like this as well? All right, what was your final answer? You got 4? Okay, 4 sounds good to me. So there it is. Well, whoop-de-doo, right? Well, this is interesting because I think the last prediction that we had was, what, 3.5 or something? It was not 4. And so this is a little bit better method. You're using more information about the function. And so actually this will be usually is a better, approximation. Let's see, go back here and see what was that other one? 3.25. It wasn't even 3.5, 3.25. So like I said, I don't have the actual value right in front of me, but let's take a look at the next method. So the order 3. And this is all you're going to do on your homework is order 1, 2, and 3, and that's it. Just some practice. It's not hard, but we'll put this into the computer on this. I know it looks the worst, but it's just that you've got another term on this Taylor polynomial. So you've got a third, so this is the third order, so you have a third degree Taylor polynomial. It'll just take me a minute to copy this over. We're doing the exact same, so the same function. So I'll put this over here. Hold on a sec. Copy and delete. So it'll take me a minute to switch back and forth. So I don't want to make you dizzy. So there it is. And let me go grab that formula just so I don't have to copy it. I know you're probably copying it, but the formula just comes directly. That is just the Taylor polynomial of degree 3. It's amazing that, these Taylor polynomials actually have something that are useful. Like when you do them in Calc 2, it just feels like, what's the point? I mean, they're kind of cool, but here they actually have something that they're useful for. Okay, that's better. So maybe I'll put that there. Okay, so we're going to use an order 3. Give me a sec. I think you can probably guess what I'm going to do now is I'm going to make a table. And on that table, I'm going to put all of this information. We've already done the second derivative, so we'll need to do the third derivative. So that's something you can do if you're really excited. You could get your third derivative for this particular situation. Give me a sec, though. So this is maybe x and y. And then this is y prime, which is 2x squared minus y. And then y double prime we did already. 4x minus y prime. Now we just need y triple prime. All right, let's see how we do. Oh, Sam, I know you know it. Where'd he go? He's got this phone call. I think he's interviewing. He's also getting a job, I guess. Oh, Breyer, do you know what the third derivative is? If this is the second derivative, what's the third derivative? Perfect. Not that bad, is it? So bear in mind that if you need to, you're going to be using implicit differentiation. This one was pretty simple. But there are some problems. In fact, I'm pretty sure that I picked one for the homework where you have a product. And whenever you have a product, you're going to have to deal with like the whole implicit like use of product rule. Just be careful with that. Maybe if we have time, we could take a look at it before we leave. I think we will. Okay, so the same thing, same prediction. So in fact, why don't you do this? Let's see, that way I'll get the actual solution so we can make comparisons. Give me a sec. First of all, let me get this set up for you. So we're going to start at 1, then you're going to get 1.5, and then you'll have 2. Your y values, you start with 2. We already know that this is going to be 0, and we know that this is going to be 4. So we've already got that information. You can do this next one, which I think is going to be pretty easy to do. and that will help you get the next line. So see how much of that you can do. I'm just going to freeze this, go grab just do this really quick, solve this differential equation. Mm-mm. Mm. Well, I just found out. Yeah, well, when I solve this, I'll show you the solution. Those of you who know differential equations, yeah, I totally just picked, wait, sorry, you can't see it. I totally just picked this. Well, I don't want to say it random because I don't believe that if I'm picking it, it's not random unless I roll dice. I should have rolled dice to get it, because an unfortunate thing happens when you do the solution. I'll show you in a minute. You probably have figured out what that unfortunate thing is, but here, let's just go ahead and fill this in. I know it's boring now because that's 0, is it not? Which means that this is basically the same as this up here. So 2.5, we've already done this, that's 2. And this one up here is also 4. And then that's also 0. So boring. And then you get 4. So if you got 4, great. You did a great job. But you can see though that you could, like, if you had something other than 0 here, it's not that big of a stretch to plug it into this. It'll make things much uglier, I guess, but yeah, here's what happened is, so those of you who know differential equations, here's how I did this one, is I took that and I moved the y over to the left side of the equation so that you had this. And I know that you're used to doing this, like the differential equations, you're used to doing this with second order differential equations, but I'm using it for a first order differential equation. R is equal to -1, which means that my homogeneous solution is c e to the -x. So if your differential equations, hopefully you're following. And then the particular solution is going to be what it's going to, here, I'll write it. I did it in my head, but it wasn't too hard. The particular solution is going to be something like this, plus bx plus c. And then you could stick this into that and figure out that a is 2, b is -4, and c is 4. So there's my particular solution. So here's my general solution. Everything's good, right? You're thinking, yeah, no problem. And now I just have to figure out what c is. And to figure out what c is, I use that initial condition, y of 1 equals 2. Well, check it out. When I plug 1 in here for x, I get c times e to the -1 plus 2 minus 4 plus 4. So I get c times e, well, e to the -1, plus 2. So what does c have to be? Here, I'll actually write it out, spell it out for you. So 2 has to equal c e to the -1 plus 2. So it's the most boring of the situations is c equals 0. So there it is. So the actual value is 4. So that was a little disappointing. Normally it's not quite that boring, but there you go. So this was, it was totally, yeah, like I said, I don't want to say it's random because it doesn't feel random when I'm choosing the numbers, but I just picked two numbers. I thought I will pick y of 1 equals 2. How hard can that be? I should have picked y of 1 equals 1, because if y of 1 equals 1, then at least c wouldn't equal 0. But we're stuck with this. So anyway, but I guess we've been saved from nasty fractions because this can get kind of ugly. So what you would do is if this was anything other than 0, you would stick it in here and you would put h cubed, which is 0.5 cubed in there, and then 3 factorial on the bottom. So that's a pretty ugly fraction. But there it is. Yeah, so you get the picture though. Okay, so let's take a peek at what have I picked for you. So here's the homework there. Let's see, can I move it over so we can see two things at once? Sure. What can I put up there as well? Don't I have some tea time? There it is. There. Oh, can't see anything now. Hold on a minute. If I get rid of that and get rid of this, now I can see it, but you can't. That's all right. Yeah, I just wanted to make sure nothing weird. Okay, you can't see either of these. So notice that I've got, well, if you could see it, you'd see that I'm asking you to do problems 1AC. This is in the next section, section 6.2. 1AC, 2AC, and 3AC. That is suspicious. You might think, why is it A and C every time? It's because 1AC has you do, there is a product. So let me help you with the product. So it has you do these two differential equations that you can't see because they're so small. But then 2 says, do it again using a Taylor method of order 2. So you'll do those just like what we just did. And then do it again for part 3 with Taylor method order 3. So basically you're just doing what we just did, but with these two differential equations instead of what I had here. Let me help you though with letter C, just to make sure that it doesn't, because letter A is going to be super easy, but letter C has this differential equation. First of all, they have a dot there. Why do they have a dot? Is equal to t times y. So I just want to help you with your derivatives. So that I don't like. I'm going to write it like this because I don't like the dot. So you do what you want to, but I'm not going to, I refuse to do a dot. Okay, let's do the second derivative. Second derivative, you're going to use the product rule. So 1 times y, yes? Incredible. What kind of idiot? Oh, I know what kind. My kind. Okay, well, anyway, there it is. So there, that better? Y prime, there it is. So I refuse to do the dot. So let me just back up. Yeah, here's what the book says. I hate the dot. I do this. And so I'm going to do the derivative of this. To do the derivative of this, you have to use the product rule. You know the product rule. Leave the first thing alone, do the derivative of the second thing, then leave the second thing alone, do the derivative of the first thing. So that's what I was about to do. I guess I was going to do so I've got 1, that's the derivative of t, times y. Leave y alone, don't touch it. And then plus t times the derivative of y. But remember, the derivative of y is y prime. Y prime. So anyway, that's the second derivative. And the third derivative I think you can handle, but just in case, well, no, I'll let you do it. You're going to, yeah, this first bit is not a problem because that's just going to be y prime. But here, do the same thing. It's a product rule. Do 1 times y prime and then do t times the derivative of y prime. You'll get it. And you can make your little table. And by the way, I think, let me just check here to make sure. I think it's the same, yes. It's the same step size. So you only do 2 steps. So it's not going to be too onerous. You do 2 steps and you'll be fine. So same step size, it'll be easy. All right, so does that do it? Any questions, concerns, fears, worries? So we'll all go to the musical this weekend. Well, at least one of these days, hopefully. All right, well, that's it. So let me stop the recording if you want to come talk. Otherwise, we'll see you on Monday, or maybe at the musical later on this tonight. So I think I'm going.